The first thing we need to do is write the objective function and all necessary constraints. Now, in this particular section, those things are going to be given to you. But when we move on, you're going to have to come up with the objective function and all the constraints, and then complete the rest of these steps. Once we've got our objective function and constraints, we graph the feasible region, and then we find the value of the objective function at each corner point. This step is usually the hardest one because you're going to have to work out where all the corner points are, and sometimes there can be quite a few of them. For a bounded region, the solution is given by the corner point producing the optimum value. By a bounded region, that means we have a border going all the way around our feasible region. For an unbounded region, we need to check that the solution actually exists. If it does, it will occur at a corner point. Now, the last thing I want to point out, if more than one optimum value exists, so for instance, there are two corner points that give you the exact same z value, and it's either smallest or largest, depending on what you're looking for, then the optimum value will occur all along the line that connects them. Let's take a look at another example. So here we're going to maximize z equals 2x plus 2y. So that's my objective function. And it's subject to the constraints 3x minus y greater than or equal to 12, x plus y less than or equal to 15, x is greater than or equal to 2, and y is greater than or equal to 5. We've been given our objective function and constraints, so now we have to graph the feasible region. So I've gone ahead and put all of these lines in, the 3x minus y equals 12, x plus y equals 15, x equals 2, y equals 5. Now, when I look at this, let's make sure everything makes sense. So the line that we have going up here in green, that's the line x equals 2. The yellow line is y equals 5, and because we wanted x to be greater than or equal to 2 and y to be greater than or equal to 5, we needed to be up here to the right and above those two lines. Now I have the line 3x minus y equals 12, which has intercepts at 4 and negative 12. That's this purple line. And then x plus y equals 15. Well, that has intercepts at a y-intercept at 15 and an x-intercept at 15. That's this magenta line. So I needed to be to the left of my magenta line because 0, 0 makes this true, and I need to be to the right of the purple line because 0, 0 makes this false, so we've got to be on the other side. Let's find some points of intersection. So let's take the line 3x minus y equals 12, x plus y equals 15. Let's eliminate the x's, so I'm going to multiply the bottom equation by negative 3 to get negative 3x minus 3y equals negative 45. I'll add that to 3x minus y equals 12. My x's go away, and I'm left with minus 4y and negative 33. So solving, I get y equals 33 fourths, and if I plug that y back into x plus y equals 15, solve for x, I get 27 fourths. So that's the point up here on the top of my feasible region. Now let's look for another point of intersection. So now I'm going to take 3x minus y equals 12 and y equals 5. Now this one's easy to solve for. Y equals 5, when I put it up into that equation, gives me 3x minus 5 equals 12. And if I add 5 to both sides, I get 3x equals 17. Divide both sides by 3, x equals 17 thirds. 17 thirds comma 5 is the corner point that I see right here. Now my last corner point is going to be where x plus y equals 15 and y equals 5 intersect, and that one's even easier because when I take and put the 5 into the equation, I easily see that x has to be 10, and that's the corner point that I see over here where the magenta and the yellow lines intersect. So I've got all of my corner points, and this is a bounded region, so the maximum is going to occur in one of these three places. So I'm going to take those three values and put them back into the objective function. So I've gone ahead and listed those three corner points out, and now I'm going to go ahead and put them in here. So for example, if I put 10 and 5 in for x and y, I see that I get 20 plus 10. 20 plus 10 is 30. If I do the same thing for my other corner points, I see I get a second value of 30 here. And for the last corner point, I get 64 thirds. So 64 thirds is around 21. So we wanted the maximum, so it occurs at these two values. Since it occurs at the same value here, that means that all along the line connecting those 2 points, z is equal to 30. When I write out my answer, I say, yep, the maximum occurs at these 2 points and on the line connecting them. Just like that. We've solved this linear programming problem.